Okay, so Brad wants me to do 7. Henry, you had your hand up as well.
9.
On that same page, 7 and 9. Okay, let's do those. Oh, I had 9 on the board and then I erased it. Lame. Okay, 7. You've got a skydiver falling. And you are told that initially the skydiver, and I'm going to call down positive for this particular scenario because that's the direction the skydiver is going in. Initially, you got a skydiver falling at 220 kilometers per hour. Eventually, it says here, before pulling the chute, if she slows to 25, so now you've got, here's your parachute. You've got, she's now falling slower. V final is 25 kilometers per hour, still down. Nothing has changed in that regard. What is the average force of air friction that acts on her during her deceleration? So it's the air being caught up into this parachute that's slowing her down. She's falling down, down's positive, but if she's slowing down as she falls, she's accelerating which way? In negative, up. So there's going to be some acceleration that way that we have to figure out. And then the question says, well, what is the average force acting on here? If the acceleration is up, because she's not falling down as fast, then that force is going to also have to be up. So everything here starts with F net equals ma. What forces are acting on her during her deceleration? Brad.
F air, resistance.
So there's going to be F air up.
And FG.
And FG is still down. Okay. So we're going to have, and if we called down positive, which I did, your net forces are going to be FG minus F air. And that's going to be equal to MA. FG is, she's 75 kilograms. So FG is going to equal MG. So that's going to be 75 times 9.8. Oh, what is that value? What's 75 times 9.8? It's going to be just below 750. 740 something? 740 what? 75 times 9.8. 735, not 740 anything. 735. So FG is going to be 735 minus the force from the air is going to equal 75 times whatever the acceleration is. And we don't know what the acceleration is. So we have to use kinematics to go ahead and find that. And we're told she slows down in 3.8 seconds. So we're going to use this kinematic information to find her acceleration. And then we're going to plug that in here and solve for the force. So V final equals V initial plus AT. This is the kinematic equation we're going to use. We have a time, we have a VI, we have a VF. We're looking for A. So VF is 25 kilometers per hour, which I have to turn into meters per second. So to turn kilometers per hour into meters per second, we're doing what? Dividing by 3.6. So I've got my free body diagram, I've got my kinematic information, I've got my formulas. 220 divided by 3.6 is 61.1 repeating. And 25 divided by 3.6 is going to be 6.94, and the 4 apparently repeats forever. Emma, good afternoon. What is your favorite kind of puzzle? Crosswords, mazes. Someone said, where's Waldo? Those little metal rings that go together that you have to move a particular way to get them out. Block Blast? What's Block Blast? I don't know. Oh, Tetris. Yeah, sure, Tetris can be... Fine. You know what? We'll Google it. Oh, it has a kind of a Tetris vibe. You know what? It's listed as a puzzle game. I'll allow it.
That's my favorite one.
Block Blast. Okay. Love it. So V final is 6.94 repeating. That's going to equal 61.1 repeating plus A times 3.8. So then the acceleration I'm going to get is going to be 6.94 repeating minus 61.1 repeating divided by 3.8. And that's going to give me an acceleration of negative 14.25 if I round it. Meters per second squared. Brad, did you get that acceleration?
Yep.
Okay. So then that value is going to go in here, 14.25. And this side is going to be negative. I want to get F air alone. So what I'm going to do is I'm going to add this guy over here. And I'm going to add this guy over here. This is going to be negative over here. So that means F air is going to be 735 plus 75 times 14.25. It's going to be much larger than 350. 75 times 14.25 plus 735 is going to be 1,803.75. I'm willing to bet you, if you got 350 for this, it was a minus sign. Because I called down negative, down positive, the upwards acceleration, this should have been negative here. So when it ends up in here, it adds to the 735. And that should be newtons. I should have units there too. And because this is positive, oh, no, I've got my direction here already. I made it negative right there. So 1,803.75. It's the force upwards on our skydiver. That make sense? Okay. You see where you went wrong? Okay. Henry. All of number 9 or just A or just B or? I mean, A and B are the same. The setup is identical. Okay, so I'll do A and then B will follow the same way. So in B, you've got a car zooming towards a wall. The car is going to impact the wall. And then the car moves back the other way. Not as fast, it only has one speed line, not 3. When in doubt, draw it all. Initially, finally, and then the in-between. Which one of these diagrams is going to have my free body diagram on it? Where does the force act on the car from the wall, as far as my diagram? Because that's what's happening here. The wall is punching back at the car, forcing it back the other way. So where should I draw my free body diagram here? The middle one, the wall one. So here in this scenario, you've got Fg down, you've got Fn up, and you're going to have the force from the wall. We could call it another normal force, but I don't want to confuse it with the normal force on the ground, because that's what it is. Whenever you've got an object in contact with a surface, we can call it a normal force. Initially, the car is headed towards the wall at 24 meters per second, that way. At the end, it's going 8 meters per second back. So we've got 2 different directions in the problem. Henry, we got to call one of them positive, one of them negative. Which way do you want to do it? Got to pick. It doesn't matter. It's arbitrary. You just have to decide whichever way the heart blows. Sorry? To the right positive? Sure. You want that way positive? We can do that positive. Hands up if you would have said a different direction. Did we not do this question? He said to the right he wanted positive. Did everyone do to the right positive? Okay. Did anyone do the other way? Every time you look at me like that, it's like you have an answer you want to keep a secret from me. You didn't do the question, okay. So sure, to the right, positive. Personally, I mean, that is not a wrong answer. To make your life perhaps a smidge easier, if you had called to the left positive, it means the thing you're looking for, the force from the wall, would have ended up being positive. But it's arbitrary. It doesn't matter. So let's go with the way you wanted it. Right, positive. So if to the right is positive, your initial velocity is 24 meters per second. What's the final velocity of the car? It's 8 meters per second to the left. So how is that going to show up in the... It's going to show up as negative. So final velocity is negative 8 meters per second. We are told that this takes 0.9 seconds to happen. And we want to know the force exerted by the wall. Well, F net equals ma. The only force acting in the direction of motion is the wall. It's the only force acting left or right. And in this case, it's acting to the left, so it's going to be negative. So we're going to get negative F wall is going to equal the mass of the car times its acceleration. We're looking for this, so it's going to be F wall is going to, or negative F wall is going to equal the mass of the car, which is 1350, times A. And we need this value for A. That value for A is going to come from this kinematic data right here. It's the same equation we used above. We've got a final velocity, we've got an initial velocity, we're looking for an acceleration, and we know the time. So VF is negative 8, initial velocity is 24, plus A times 0.9. So I'm going to subtract over the 24, we're going to get negative 32 is going to equal A times 0.9. So 32, negative 32 rather, divided by 0.9 is going to be 35.5 negative 35.5 repeating meters per second squared, and that's the value that goes in there. So negative F wall is going to equal 1350 times negative 35.5. So I'm going to multiply both sides by negative 1 to get rid of these two negatives. And you're going to find that the force from the wall is going to be 1350 times this. Oops. I added a bracket where I should not have added a bracket. 50,000. Did I oops that? Eight plus 24, that's 32, divided by 0.9, yeah. Times 1350. Oh, yes, I punched something into my calculator wrong. That's 4,800. Sorry, I said it again. 48,000 is the value there, or 4.8 times 10 to the 4. So that's the procedure for this, assuming you can use the calculator properly, which clearly I was not. Henry, does that process make sense?
Yeah.
So part B is the same. Part B says, or it's similar, if the same car had no crumple zones. So instead of this car being made in the 2000s, it's made in the 70s. This car does not crumple. It's a solid metal box. Now the time for impact is lessened. That's what crumple zones do. They increase the time of impact. So if we're decreasing the time of impact down to 0.08 seconds, the only thing, Henry, that changes is this value right here. This gets smaller, so that's going to make the acceleration larger. Because you divided 32 divided by 0.9. Now it's going to be 32 divided by 0.08. That's going to make this acceleration much bigger. So when you multiply it by the 1350 down here, it's going to make your final and the force from the wall that much larger. It should be 54,000. The 5.4 times 10 to, sorry. I misread again. 540,000. Which is why crumple zones are a thing. Because 540,000 newtons of force on the occupant of a car is way more devastating than 48,000 newtons of force on the occupant of a car. Comments, questions, concerns? Henry, does that make sense? Okay. We good? Okay, comments, questions, concerns on anything else I assigned to you for homework? The only way you guys are going to get a handle on this stuff is if you practice it. If we're not choosing to take the time to do that, or if you didn't have the time to do that, then it's going to be difficult for you when I give you a test on this stuff. Does anyone want me to go over any of the questions on this page? So either it was easy or we didn't do it. I don't know. Let me know if you've got comments, questions, concerns when you do decide to go back and take a look at these questions. Today's lesson isn't very long, so perhaps you'll have time to go back and do them today. If there are no other questions, find me this page right here. So we've done Newton's second law, and we've done Newton's first law. The first law was an object in motion is going to remain in motion, an object at rest will stay at rest unless acted on by an outside force. The second law was that a net force acting on an object is going to produce an acceleration, or another way to read it, the net force is equal to the mass times the acceleration. And today, Newton's third law is probably the one that you're more familiar with than the second. Does anyone know the law we haven't referenced yet? There's only one more. Maybe if I start with the words for every action. For every action, what? Yeah. And there's a couple important words you left off, Brad. For every action, there is a reaction. Well, that is true in so many areas of life. We need to specify in physics that for every action, there is an equal and opposite. Those words are important in physics. It's true in every area of life. You do something to someone, they will respond somehow. In physics, the reaction is always equal to and opposite the original action. For every action, there's an equal and opposite reaction. And again, this is something we don't often think about. How many of you, when you watch a movie where someone punches someone else, do you ever sit back and go, oh, the guy who just did the punching just broke his hand? Has that thought ever occurred to any of you? Okay. Some of you, yes, some of you, no. Lots of us, we watch the movie, someone get punched in the head. Now the person who got punched in the head is on the ground, perhaps they're unconscious, and we're like, oh, that sucks for that person. Very rarely do we actually step back and think, no, the person who just punched skulls are hard. Like, knock on yours, it's hard. If you punch someone else in this, especially at your guys' age, your skulls harden and they finally solidify at your late teens, early 20s. Babies' heads are soft so that they can be born. My son has kind of an oddly shaped head because he slept on it, and then it solidifies over time. Skulls are hard. You punch a skull with a bare hand, you've got a whole bunch of joints in here, call them knuckles, and those aren't as hard as the skull that they're punching, and often as a result, they will break. Often you'll see people will have broken their hand, but rarely do we think about that. And that was the idea behind Newton's third law. Not that you watch someone punch someone, they're going to break their hand, but that's an example of these ideas here. Every interaction involves two forces that we call action-reaction forces. And it's important to recognize what those are and treat them appropriately. These pairs of forces Always act on both objects. I don't have enough space there, so I'll put it below the line. And when this happens, we often only think about one of the objects, because in all of these things, that word right there is reaction, R-E-A-C-T-I-O-N. Reaction. My apologies, Kai, for my penmanship, if that is the issue. Any baseball players in here? Okay. When you hit a bat with a ball, again, if you're just watching the sport, they make it look so easy. The ball's coming in, the bat gets swung, the ball goes for a ride, the guy flips the bat in the air and walks to, maybe he's all the way around the bases. They make it look really easy. But anyone who's ever hit a bat with a ball, you feel it. The impact is not just ball on bat, it's not bat on ball, it's also ball on bat. And in an aluminum bat, the whole thing vibrates. And if you're not holding onto the bat tight enough, it actually quite hurt. So we wear batter's gloves. That's why if you've ever played baseball, you're told to hold the bat very tightly so it doesn't get knocked out of your hands. And it hurts. It's uncomfortable. First time a child does it, it's uncomfortable. So you get the bat hitting the ball, and everyone cheers. But nobody stops to think about the ball actually hits the bat. And why do we ignore the effect on the bat? Well, it's because it's not as noticeable. Unless you're the person swinging it, you don't notice it. And what's the reason for that? What does the bat have that the ball does not, or that the ball has less of? Mass. We often ignore the thing of lesser mass. The ball has less mass, so the effect is greater. And when the effect is so great, someone hit a home run, we ignore the fact that the bat itself just took a beating of its own. A sprinter starts to run. How do you move? How do you run forward? If you're on a track, you don't often see this, but if you're on dusty ground, it's easier to see. From a standstill, you start to run. How? You push off the ground. So the runner pushes the ground, but that doesn't actually make the runner move forward, because the runner is just pushing backwards. What has to be happening for the person to go forward? Well, something has to be pushing forward. When you run, you're not making the earth spin under your feet. So the you pushing back can't be the only thing. So what has to be pushing on the runner? The ground. The friction between the ground and the runner. The ground pushes on the runner, and that's why the runner goes forward. You don't spin the earth. The earth pushes you forward. And then a fish swimming through water. How does a fish swim? Sorry? What does it do with those fins? Well, so the fish is just doing this. But how does the fish go that way? Okay, so the tail goes back and forth. Tail's going back and forth. So if I'm the fish, you see my tail doing this. How does it move me this way? Well, that just means that the water goes backwards. If I'm the fish pushing the water, that just means I should be stationary and the water should be moving towards you. The only way for the fish to go forward is if the water is also doing what? Pushing back on the fish. You don't see the water move because the water has so much more mass. The fish moves because it has less mass, but there's a push both ways. If the water doesn't push back, the fish doesn't move. So the fish pushes the water. I should just say fish, not fishes. The fish pushes on the water. And if that was the only thing that would happen, fish stays stationary. If you want to take her the beverage, feel free. If she is welcome to the beverage, do what you got to do. Because I know every time I look up, I'm witnessing the end of another part of the conversation. I don't mind. Do what you got to do. If she wants a drink, give her a drink. Fish pushes on the water pushes on the fish. That's the only way that happens. So Newton's third law, again, we only really notice the effect on the object of less mass. We don't notice the Earth spinning because you're running. The Earth is so much more massive, so it pushes you and you do nothing. We don't notice the water getting pushed backwards by the fish. We just see the fish propelled forwards. The fish has the less mass, the effect is greater. Let's do a practical example of this, and then I've got a story for you. Well, not so much a story as a science paper I'm going to read to you. So let's imagine a bug hitting the windshield of a semi-trailer. Happens all the time. What force pair occurs when this happens? What's the effect of the bug hitting the windshield? Okay, so you have bug hits windshield, and you've got windshield hits bug. Which one of those has the bigger effect? The windshield hitting the bug. When the windshield hits the bug's front goes through its back. And now you've got this thing splattered everywhere. This is an extreme example. We've got a really small object hitting a really large object. Is there a noticeable effect on the truck? No. Well, the truck gets dirty, but it's not like you're driving down the road and all of a sudden, bam, you smack a bee, and then like the truck shakes because you just smashed a bee. No, the truck is going to keep going. There's going to be zero noticeable effect if you're on the inside of that cap. If you're the bee, now you're at the pearly gates of whatever bees call heaven, and someone's explaining to you what just happened. But there's no measurable effect on the truck. Well, or is there? If we made the object larger, let's say it wasn't a bug, it was a moose. Moose is much larger. You're driving down the highway in your semi-truck and you hit a moose. All of a sudden, that's a whole heck of a lot more noticeable, right? Truck hits moose, but moose also hits truck. Right, Mr. Keeley? You ever hit a moose? You're not dead, so you know you haven't, but
I haven't, but my grandparents
it's terrifying.
have. Not a moose, but a deer.
Well, the moose is terrifying, because the moose, you hit the legs and then its body lands upon you. Yes, moose is terrifying, which is, nah, not a moose. So bug hits windshield, no noticeable effect. Moose hits semi-truck, all of a sudden now that semi is going to take some of the impact. Now the semi's not going as fast anymore. And so, but the moose has mass, the bug has mass. The fact that the moose had a more noticeable effect just means that it was because its mass was larger, but the bug still has mass, so there has to have been some effect on the truck, and we're going to look at what that is. Yeah, Brad?
What's like a semi-truck? It's like something like really tall. Like wouldn't it just get like pushed under after a while, or just the side?
Well, a moose is, if you've never seen a moose is very tall. If a semi-truck hits the moose, it's going to end up in the cab.
How tall are they?
Oh no, the legs are 6 feet long. The legs are 6 feet tall. And that's where the rest of the body starts.
Oh, I didn't know they were that big.
I have a buddy, he's roughly my size, a little small, like height-wise, a little smaller than me. And he shot him, he's a hunter, and he shot a moose and he sat on it and he could not touch the ground on either side of the the neck. He sat on the shoulders of his dead moose to take his picture, as hunters do, and his feet were not touching the ground on either side of the moose. They are massive animals. We don't think about it because we don't see them very often, but if you've ever done BC to Alberta, you have a pretty good chance of seeing one. That drive, I mean. So, which force would be larger? If every action has an equal and opposite reaction, which force should be larger? Brad. If every force has an EMF, what are you going to say? You're going to say, well, it doesn't matter if it's the moose or the bug. Both have mass. Both masses are smaller than the truck. Which one's going to feel it more? The bug or the bug/moose or the semi-truck? Is that what Newton's law says? The forces are going to be equal. Well, why is one dead and the other one not? The semi-truck will survive both impacts. The animal will not. Let's look at why. Which force is bigger? They should be the same. Newton's law says that neither force is bigger. Both are the same. So let's look at what happens here. If they're both equal, let's set up F net equals MA for both. Let's say that the force on the bug is going to equal the force on the truck. And if you want, I can do the moose on the board just for you quickly afterwards. Well, if F equals MA, then this is going to be the mass of the bug times the acceleration on the bug, and that's going to equal the mass on the truck times the acceleration on the truck. Well, the mass of your average bug, I don't know, give me a bug. What kind of bug are we going to kill? A fly? Mass of horsefly. Mass of a horsefly is, oh no, I don't want it between, just give me a number. 12 milligrams. Okay, so what is that? 12 mg/g. No, I want that in kgs. So the mass of this bug is going to be 0.0000, 1, 2, 3, 4, yeah, 1, 2. And that's in kilograms. 0.000012 kilograms is your horsefly. Those of you who've never had the misfortune of meeting a horsefly, they're awful. Mass of the semi-truck. According to Google's AI, when loaded with cargo, a semi-truck's mass or weight can increase significantly with a maximum legal gross vehicular weight around 80,000 pounds, which is in kilograms 36,287. So that's the mass of a fully loaded semi-truck, the maximum legal mass of a fully loaded semi-truck. Now, let's figure out what the acceleration is on the bug. Let's say the fly was stationary in the air. VI is 0. VF, let's say that the semi-truck driver was doing something semi-truck drivers never do. Let's assume he was driving the speed limit. Having known many in my life, they don't. But let's assume that he was. She was. They were. Whoever it is. So speed limit on the highway, 100 kilometers per hour, which I'm going to convert right away into meters per second. Divide 100 by 3.6, and we're going to get 27.7 repeating. So let's call that 28 meters per second. They were speeding ever so slightly. Semi-truck drivers never do this. How long would you say it takes the horsefly to go from stationary to the speed the truck is traveling at when they impact each other? How quickly would you suggest it takes the fly to go from 0 to 100 kilometers per hour when the truck impacts it? What do you mean? It can't be instant. An amount of time has to have passed. I'm just looking for a ballpark here. Like nothing is instantaneous. Everything takes time. I mean, I'd even say it could be less than that. 1/100th of a second, a millisecond. Well, I mean, imagine being hit by a semi-truck. You're standing there and it plows into you. How quickly does it take for you? How much time does it take for you to reach the speed the truck is traveling at when it picks you up on its way by? Oh, flying by itself. That never would happen. No, on impact, how much time does that take? Kai is suggesting a 1/100th of a second. Okay, so let's say that. Time is 0.01 seconds. So then let's figure out what the acceleration has to be for that. Well, that's going to be VF equals VI plus AT. VF is going to be 28, is going to equal A times 0.01. That acceleration is then going to be 28 divided by 0.01. That's an acceleration of 2,800 meters per second squared. Based on the kinematics here. So we're going to take that value, we're going to plug it in for the acceleration of the bug. And we're going to figure out what the acceleration on the truck is. The acceleration on the truck is going to be, because the forces are equal and opposite, we're going to have this mass, 0.000012 times 2,800 divided by 36,287. It means that the acceleration on the truck is going to equal 0.0000006 zeros 93 meters per second squared. The forces are equal and opposite. The accelerations are decidedly not. So it's not the force that kills the bug. What is it? It's the acceleration that the bug undergoes. The acceleration on the bug caused by the truck causes the thing to disintegrate. There is an acceleration on the truck, but it's so small, it's not noticeable. Yeah.
So like if I got hit by a semi-truck 100 kilometers an hour, the acceleration from me going from stationary to 100 kilometers an hour, that would kill me instead of just.
It's the acceleration that kills you, yes.
Hey students, if you have not voted yet today, please make your way to the learning commons.
You had your chance. No one goes votes.
Voting will close at 2.
Ray, yes, say again.
Thank you.
I just solved this equation. I did kinematics to get the acceleration on the bug. So this times this divided by this gives me the acceleration on the truck. The only assumption we made, the only guess we made, was how long it takes the bug to come up to speed. If this is quicker, this number will get bigger, this number would get slightly bigger. But, I mean, look at these values. This is on the neighborhood of, that's the centimeter per second squared, millimeter per second squared. Like, we're talking about like 900 nanometers per second squared. Like it's such a small number. This is why you would say, yeah, this isn't measurable. So let me read you something. I find this hilarious. You might not. So this might introduce you to something brand new. BB gun train. There's a website that I used to frequent called XKCD. Hands up if you've ever heard of XKCD. Unfortunately, none of you. That's really sad. Lots of the posters I have in my room come from this website. That money poster on the back comes from this website. Over behind the ladder, there's a gravity poster that comes from the website. The Gravity Well poster up at the front, my Apollo rocket or the Saturn V rocket over there, all come from this website. It's written by a former NASA engineer, and he, in addition to the comics that I find amusing, he's written several books, and the books are all called What If. And people write into him, again, former NASA engineer, they write into him and they say, what if? So, that's what I'm going to read you now. Charles James O'Keefe wrote into this guy and said, in the movie Armageddon, hands up if you've seen the movie Armageddon. Guys, come on. 90s disaster movies, go watch Armageddon. In the movie Armageddon, a NASA guy comments that a plan to shoot a laser at an asteroid is like shooting a BB gun at a freight train, which is effectively the question we just did. Horsefly on semi-truck, BB gun on train. That's the question. What would it take to stop an out-of-control freight train using only BB guns? That is the question that someone wrote into this guy, and here's his response. First of all, for the record, shooting asteroids with lasers is a great way to deflect them. Stopping a train with a BB gun might be harder. A Red Ryder spring piston lever action air rifle fires a .177 caliber, 0.33 gram steel BB with a muzzle velocity of 100 meters per second. That's how fast the BB is moving when it leaves the gun. And it's 0.33 grams, so it's much larger than this horsefly. Oh no, it's actually similar in size to the horsefly. It's like 3 times the size of the horsefly. Not much bigger. The GE Genesis Series 1 locomotive weighs 12 metric tons and travels at 45 meters per second. So that's a large train. If you bounce a single BB off the front of the locomotive from point blank range, you will slow it down, he does the math, by about 1 foot per day. So barely. The effect on the train is noticeable over the course of an entire day, but it's slow. At 1 shot per second, it would take 2 days and 200,000 BBs to stop the train. And by this point, the train would have stopped on its own anyway due to the drag on the train. Clearly, the Red Ryder isn't cutting it. It's time to wade into the terrifying world of hardcore air rifle enthusiasts. The Tactical Edition Drozd Blackbird is a high-end BB machine gun. It fires 1,200 rounds a minute at a muzzle velocity of 200 meters per second. At these speeds, standard BBs are capable of breaking bone. Unfortunately, even instantaneously emptying the full 600-round magazine into the front of the train would only reduce its speed by a small fraction of a percent. A single person with a BB gun can't do it, but what if we had an army? We'll give each person a patch of ground 2 feet by 4 feet. It's a little cramped, but it should give them room to fire in an arc over the shoulder of the person in front of them. So basically what they're doing, this is about 2 feet by 4 feet. We'll put a square around him, a square around him, and I'm going to be back here, and I'm going to have my BB gun machine gun, and these guys are going to have their BB machine guns, and all of us are in an arc in front of the train, shooting at the train with BB guns, trying to bring the thing to a halt. If we restrict them to a 45-degree arc in front of the train on either side, we can pack about 100 people within 10 meters, 300 people within 20 meters, 550 within 30 meters, and another 750 within 40 meters of the front of the train the instant we start firing. Most of the shooters are able to hit the train fairly straight on, integrating the momentum from all the different angles. It would exert about 90% of the total force, given an ideal arrangement. BBs experience a lot of drag, so the shots from those further away will reach the train slower. With that in mind, let's look at what happens when a crowd of people with BB machine guns tries to stop a train. In fact, people have 2 arms, so let's have them dual wield. So everyone is now dual wielding, like Scarface, BB machine guns. At time 0, people within 50 meters of the train, all 2,500 of them, pull the trigger, unleashing 100,000 BBs per second into the air. As the train plows ahead, people in front fly sideways off the track. As those people stop firing, people back down the track, come into range and start shooting. The train is moving so quick that any one person really is only able to get a few dozen rounds off before the train moves past or through them. At any given time, there's 45,000 BBs in the air, but there's a problem. When the steel balls bounce off the front of the train, they don't disappear. They bounce back into the cloud of BBs coming at them. At its peak, the cloud of ricochets deflects about 1% of the incoming shots. It's a neat effect, but doesn't actually really substantially interfere with the plan to stop the train with the BB guns. Unfortunately, even this hail of steel takes several minutes and almost 2 kilometers of track to stop the train. Means we would need over 100,000 shooters lined up along the track, and arming them would cost in the neighborhood of about $50 million. If you had 100,000 people dual-wielding machine guns, BB machine guns. But we can do better if we relax the BB requirement. Does anyone know the world's most common rifle? What is the most common automatic weapon found on the planet? The AK-47, you betcha. Here we go. The AK-47 has a muzzle velocity of about 715 meters per second and fires a bullet which outweighs a steel BB by a factor of about 25. A bullet on an AK is about that big. I have shot it. It's about yay big. The mass is about 25 times more than that of a BB. The bullet goes so fast that they penetrate into the body of the train, which means they're less efficient at slowing the thing down, but it doesn't really matter. Calculations show that a crowd of 2,500 people firing 2 AKs each would be able to stop the runaway train within 30 meters.
Why would it be less effective if it pierces the train and let it slow down just as much as bounce off?
No, because the bounce, you're maximizing the collision time with the bounce. Tearing through the object does damage to the train, but doesn't actually cause it to stop. Right. Not for very long. Not for very long. Yes, you bet. And it would only take, within 30 meters and a second and a half. They could bring a train, remember the initial speed of the train was 45 meters per second. It would take 2,500 people, so 5,000 AK-47s, 30 meters and 1.5 seconds to stop the train. So here we had one bug and the semi-truck. What if it was a whole cloud of bugs? What if the bugs weren't stationary? What if they were actually flying at the semi? It means these bugs could bring this semi to a stop as well. It's not just the effect of one on the other, it's the effect of the other on the one as well. They go both ways. It gets more interesting here. And I'll finish reading it to you. The greatly reduced drag coefficient of machine gun ammo compared to a steel ball bearing means we can shoot from a further distance. Rather than being limited by our space with the BB guns, we can go further back. Let's make the crowd 200 meters deep instead of 50. So we have 2 football fields worth of people holding AK-47s shooting at the train. 40,000 people open fire. A typical AK-47 has a 30-round magazine and fires 10 shots per second. Within 1/3 of a second, a quarter million AK-47 bullets would be in the air. Stray shots, no doubt, cause lots of fatalities in the front of the crowd. As you said, the guns are going to move as soon as you start firing them. But with trained and a disciplined group of shooters, the bulk of the shots could actually manage to hit the train. At 15 milliseconds, the train has moved 1 inch this far and has encountered the leading edge of the bullet cloud. At 30 milliseconds, the train is being hit by 6 new bullets every millisecond. At 150 milliseconds, the locomotive has crawled forward about 6 meters, and it's absorbing several hundred bullets every millisecond. This has begun to slow its forward momentum and tear it apart. But let's assume it's loaded with some kind of lightweight material that distributes the shock of the bullet evenly, like sand. Except sand's not that light, but whatever. At around 300 milliseconds, so 3 seconds, a full quarter of a million bullets, did I do that right? No, I didn't do that right. At 300 milliseconds, so 0.3 seconds, the full quarter of a million bullets are in the air, and most people have gotten off 6 shots between their 2 guns. Interestingly, the bullets from the front of the shooters occasionally catch up with and collide with slower bullets from people that shot from behind them, which is a weird effect. Doesn't happen a lot, but it happens. The locomotive now moves forward 7.5 meters, 7.5 meters, 7.75 meters, and then starts to slide backwards. Not only have you stopped the train, you've actually managed to get enough bullets going at this thing that the train is itself now moving backwards because of the impact of the AK-47 ammo. At 1 second, 1 million shots have been fired. The locomotive is sliding backward at 100 meters per second, which is just ridiculous, which is 220 miles per hour. So you had a truck that was going, sorry, you had a train that was going 45 meters per second forward, and now it's going backwards at 220 miles per hour in the span of 1.5 seconds. And all it took was, where's the number of people? I mean, the number of AK-47s necessary already exists on the planet. We just have to get them to an empty rail area. The AK-47s are made. At this point, the drag from the atmosphere is the dominant force on the locomotive. The rear end of the train lifts into the air, and it finally disintegrates into a cloud of shrapnel and bullets. So that is all to answer the question, shooting a BB gun at a freight train. Would that do it? No. But enough of them, and if you made the gun slightly bigger, would. The effect is there. And so I like read, whether you followed it or not. And if you're interested at reading more of these things, there's hundreds of them. Google XKCD, the letters together, followed by the words what if. XKCD what if will give you more of these kinds of scenarios.
Like, how do you know that people in front of you, the bullets are going to hit each other?
Because if you're standing way back, muzzle velocity, now the bullet's going to start to slow down as soon as it leaves the gun because of interaction with the air. So if you're behind me and you shoot over my shoulder, and at the instant your bullet flies over me, I pull the trigger. When my bullet leaves the barrel of the gun, because your bullet's already started to slow down due to drag, my bullet's going faster because it hasn't experienced the air yet. And so your bullet, I could actually shoot, theoretically, your bullet out of the air with my bullet because yours is slowed down and mine's going at full muzzle velocity.
But the bullets are like
no, but it is, but it's not. It's not a fake scenario. This scenario is entirely doable. We would just need to find a country large enough with empty space and a rail line with a locomotive. We could do this in the desert in Nevada. You would just need to get enough people. You're talking about 100,000 people. You're telling me you couldn't find 100,000 if you went on Reddit and put out, hey, we need 100,000 people to dual wield AK-47s for an afternoon. You're telling me we couldn't get those people? Absolutely, you'd get those people coming to the desert in Nevada to dual wield AK-47 seconds and watch AK-47s and watch a train disintegrate in front of them. I would go. Absolutely, I would respond to that ad. So we just, it's theoretical, but it's not impossible. This is absolutely doable.
Does the thing say 30 meters of ground is what it covered? The AK-47?
The train moves forward 7.5 meters from the time the bullets start to fire.
So how many people, like the distance that they were lined up, like how, what was that?
200 meters deep.
Or 200 meters.
Okay, here's what I want you to do. You have 2 sets of questions and a whole weekend to do them. Honestly, you could get them done in the 4 minutes. There are 4 scenarios. I know I didn't finish the thing, but the lesson, but that's okay. It's 3 examples of action reaction. You think you can do it? There are 4 scenarios. This guy, these guys are question 3, and this guy. In each one of these scenarios, I want you to give me every force and reaction force pair in all of those scenarios. For example, these bottom 3, and then the bell's going to go. When you pull the trigger on a gun, if none of you have shot a gun, you should, it's a lot of fun. The bullet goes forward, yes, but the gun comes back at you. It hurts. Bullet goes forward, but gun comes back. There's an action-reaction pair there. Bullet goes, gun goes back. When you break a brick with your hands, it hurts. The brick hits you back. And when you launch a rocket, yes, the gas pushes the rocket forward, but the rocket pushes backwards on the gas. So those 4 questions, I want you to give me all of the action-reaction pairs on the next page. And that's your homework for today. Have a great weekend. You realistically probably could get it done in the next 2 minutes. When the bell goes, you may also go. Have a super duper day.
Did you mark my test?
Every force has an equal and opposite reaction force.